Let me tell you something honestly. Most people don't quit microcontrollers because it's hard. They quit because it's confusing. You start with excitement, you buy a board, you blink an LED, and you feel like, yes, I'm doing it. But then suddenly you hear word like GPIO, PWM, ADC, UART, SPI I2C, and everything feels scattered. No connection, no clarity, and slowly you stop. Not because you can't learn, but because nobody explained the foundation properly. So, in this video, I'm not going to just teach you, I'm going to help you understand the thinking behind everything. By the end, you won't just know terms, you will know how things actually work. Let's start from zero. Imagine you are building a smart home. You have lights, fan, temperature sensor, door lock. Now think, who is controlling all of this? Who is deciding when light turn on, when fan speed up, when door unlocks? That brain is microcontroller. But here is where people misunderstand. Microcontroller is not just a chip, it's a system. Inside it, CPU, decision making, RAM, temporary memory, ROM, program storage. But the real power comes from something called peripherals. Now, instead of memorizing, let's understand. Think like this: GPIO is hands, ADC is senses, UART is communication voice, timers is internal clock. Without this, the microcontroller is just sitting idle. And here's the most important thing you must remember: these concepts never change. Arduino, ESP32, STM32, different boards, same concepts. So don't chase boards, master the concepts. Now let me remove one big myth. You don't need expensive tools. When I started, I didn't have a lab. I didn't have advanced sensor. I had one board, one LED, five wires. And honestly, that's enough. Because learning microcontrollers is not about how many components you have. It's about how deeply you understand one component. If you can understand one LED deeply, you can build anything. Start small, go deep. That's the strategy. Comment what board you are using. Let's go into the first and most important concept, GPIO. But instead of definition, let's start with a real situation. You connect a button, you press it, nothing happens. You press again, still nothing. Then suddenly it starts working randomly. Sometimes on, sometimes off, sometimes flickering. Why? Because you didn't understand GPIO. Now let's fix that. GPIO means general purpose input and output. Simple meaning, a pin that can either read signal, send signal. Now let's go deeper. When you connect a button, you are reading input. But here is the hidden problem. When button is not pressed, what value should it read? There's no connection. So the pin becomes unstable. This is called floating. Floating pins give random values. So your system behaves randomly. Now we fix this using pull up and pull down. Understand this clearly. Pull up is default high. Pull down is default low. So now, even when button is not pressed, you get a stable value. Now let's go to the output. You connect LED. You send high, then LED will on. You send low, then LED will off. But here is another mistake beginners make. They connect LED directly, no resistor. This can damage the pin because GPIO pins have current limits. Now, another real world issue, when you press a button, it doesn't give clean signal, it bounces. So, microcontroller reads multiple presses. That's why we use debouncing. So, now GPIO is not just input or output, it includes stable inputs, safe outputs, signal behaviors. That's why this is the foundation. Now imagine this. You turn on an LED, it's fully bright. You turn it off, it's gone. But what if you want medium brightness? Microcontroller can't do that directly because it only understands 0 and 1. So we use a trick, PWM, pulse width modulation. We turn on and off very fast, but change on time. This on time is called duty cycle. More on is brighter, less on is dim. Now real world applications are fan speed control, motor control, LED dimming. But here is something important. If frequency is too low, you see flickering. So PWM is not just on and off, it's timing control. That's why timers are connected to PWM. Let's tell me in comment. Have you ever tried LED dimming before? Now imagine you build a temperature system. Sensor gives voltage, but microcontroller doesn't understand voltage. It understands numbers. So we convert analog to digital. That's ADC. For example, 0 volt is 0, 5 volt is 1023. Now here is depth. Resolution is accuracy and sampling rate is speed. And here the reference voltage is range. If resolution is low, you lose precision. If sampling is low, you miss chances. ADC is how microcontrollers feel the word. Let's not rush communication. Let's start with a simplest one. UART. But instead of definition, imagine this. You connect your microcontroller to your laptop. You open serial monitor and suddenly you see data printing, temperature, values, messages. Have you ever thought, how is this data actually traveling? That's called UART. Now let's simplify. UART stands for Universal Asynchronous Receiver Transmitter. Ignore the big name, think of it as simple serial communication. There are only two important lines. TX means transmit to sending the data. RX is receive to receiving the data. Now here is something very important. UART sends data bit by bit, not all at once. One by one, like typing a message. Now here is where it gets interesting. Both devices must agree on speed. This is called baud rate. If one device sends fast and the other reads slow, data get corrupted. That's why baud rate must watch. Now let's go deeper. Each data is sent in a frame. Start bit, data bits, optional parity, stop bit. This ensures proper communication. Now, real world examples are serial monitor, GPS modules, Bluetooth modules. Now, common mistakes beginners make: wrong baud rate, cross connection mistakes, TX to TX instead of TX to RX. So, always remember TX should go to RX and RX should go to TX. UART is simple but extremely important. Have you ever faced garbage values in serial monitor? This usually baud rate mismatch. Now let's move to the faster communication SPI. But again, let's understand those situation. Imagine you have a display model and you want very fast data transfer. UART is too slow. So we use SPI. SPI stands for Serial Peripheral Interface. Now SPI works differently. Instead of two wires, it uses multiple lines. MOSI, master out, slave in. MESO, master in, slave out. S clock for clock. SS, slave select, or even we use CS, chip select. Now, don't panic with names. Let's simple. There is one master and one or more slaves. Master controls everything. Clock is generated by master and communication happens in sync. That's why SPI is fast. Now, real world examples are OLED displays, SD cards, sensors. Now, important concepts are slave select or chip select. If multiple devices are connected, master should chooses which one to talk to. Now common mistakes are wrong wiring, not handling multiple slaves properly. So SPI is fast, reliable, but uses more wires. Now let's go to the most used protocol, I2C. This is very important. Imagine this situation. You have temperature sensor, display, RTC module, and you want to connect all of them using minimum wires. That's where I2C comes in. I2C uses only two wires, SDA for data, SCL for clock. Now here's the beauty. Each device has an address, so master can talk to any device just by calling its addresses. This is like a group chat. Everyone is connected, but only one responds at a time. Now, very important concept, pull-up resistors. I2C lines require pull-up resistors. Without them, communication fails. Now, advanced concepts are clock stretching, voltage mismatch, arbitration. Don't worry about depth now. Just understand basic. Real world usages are in sensors, displays, RTC. Now compare UART, SPI I2C. UART is simple, SPI is fast, I2C is flexible. Each has its use. Which one sounds easier to you? Either UART, SPI, or I2C? Now let's talk about something powerful. Interrupts. Imagine this, you are studying, focused. Suddenly someone calls your name. You immediately stop and respond. That's called interrupt. Instead of checking continuously, system reacts instantly. Now inside microcontroller, when an interrupt occurs, it jumps to a specific function called ISR, interrupt service routine. After handling it, it returns back. Now important concepts are priority, latency, race conditions. For examples, button press, sensor trigger. Interrupts make system efficient. Now timers. This is like the internal clock used for delays, countings, PWM. Now key concepts are counter, compare match, prescaler. For example, blink LED every 1 second. Generate PWM. Timers are everywhere. Now let's talk about something that most beginners ignore, power. But in real world system, power is everything. Let me give you a situation. Imagine you built a device that runs on battery, maybe a smart sensor or wearable or an IoT system. Now, if your microcontroller keeps running fully active all the time, battery will drain very fast. So, what do? We don't keep it active, we let it sleep. Yes, microcontrollers can sleep, and not just one type of sleep, multiple levels: light sleep, deep sleep, standby modes. Now think of it like this. When you are not doing anything, you don't run, you rest. Same idea. Microcontrollers shut down unnecessary parts to save power. Now important question is, if it's sleeping, how does it wake up? Good question, right? It wakes up using interrupts, timers, external signals. For example, button press wakes the system. Timer wakes system for after a delay. Now real world usages are smartwatch, IoT sensor, remote devices. Now one important concept is power versus performance. If you save more power, you reduce performance. So always balance. Now beginner mistake is not using sleep modes at all. Keeping system always on. That's inefficient. So from today, whenever you design something, ask yourself, can this sleep? Think of one project where sleep mode can save power. Now, let's start about something very interesting and very important in real world system. Watchdog time. Let's understand with a story. Imagine you are running a system and suddenly your code gets stuck. Maybe infinite loop, maybe bug, maybe hardware issue. Now your system freezes, no response. In real time, this is dangerous. Imagine this happens in medical device, car system, industrial machine. So what do? We add a watchdog. Think of it like a supervisor. It keeps watching the system and it expects a signal from your code saying, I'm working fine. This signal is called feeding or kicking the watchdog. Now, if the watchdog doesn't receive this signal within a certain time, it assumes something is wrong and it resets the system. Automatic recovery. Now, important concept: timeout period. You must set it properly. Too short is unnecessarily resets. Too long is slowly recovery. Now, beginner mistakes are forgetting to reset watchdog, wrong timeout configuration. In real world, examples are embedded systems, automotives, IoTs. So, watchdog is like a safety guard for your system. Now, let's talk about the final concept: DAC, digital to analog converter. We already saw ADC, which converts analog to digital. DAC does the opposite. Now imagine this: microcontroller generates numbers 0, 1, 2, 3. But what if you want to generate a smooth signal like sound or waveform or voltage output? That's where DAC comes in. It converts digital values into analog signals. Now, simple example: if you give increasing digital values, that creates a smooth rising voltage. Now, real world applications are audio output, signal generation, control systems. Now, important concepts are resolution for smoothness, sampling rate for speed, linearity for accuracy. So, we compare DAC versus PWM. PWM also creates analog like output, but it's not truly analog. DAC gives actual analog signal. Now beginner mistakes are confusing PWM with DAC. So remember, PWM is simulated analog and DAC is real analog. That's the key difference. So now take a step back for a second and look at what you have just learned. GPIO, PWM, ADC, UART, SPI, I2C, timers, interest, power management, watchdog, DAC. These are not just topics. This is the foundation of every embedded system. And here's the truth. If you understand this deeply, you can work with any microcontroller, Arduino, ESP32, STM32, anything. Now from here, we are not stopping. This is just the beginning. I'm starting a full series on this channel, Byte and Build, where we will go step by step from basics to real projects to advanced systems. So, if you want to actually build, not just watch, do this right now. Subscribe to Byte and Build and save this playlist because this is not just one video. This is a complete journey. And trust me, if you follow this properly, you won't just learn microcontrollers, you will start thinking like an embedded engineer. And one more thing, comment start in below comment section because I want to see who is actually serious about building. Let's grow together and let's build together. Thank you.